Welcome back. We are in CS4510, L03B. The topic of today is the pumping lemma. Specifically for regular languages. There's other pumping lemmas. The pumping lemma for regular languages is basically an argument to describe what can DFAs not do. We know a lot about what DFAs, NFAs, regular expressions, and even GNFAs can do. But in fact, there's a lot of things they can't do. If you think about it, this thing has a very limited capacity, okay? It can only keep track of a couple things at once. It's got the memory of a goldfish. And there are certain problems that appear to require more memory than this thing can keep track of, right? An example, and we'll prove it today, is in fact there is no DFA for a language of the form A to the n, B to the n. N is an integer. This is any string of A's and B's where there are exactly n A's and n B's, and all the A's come before all the B's. And this is in fact different than A star, B star. You can make a DFA for the second one. Just check that A's come before B's. But there is no way for you to ensure that exactly n A's is exactly equal to the number of B's using just a DFA. Intuitively, you have finitely many states. Suppose you have like 10 states. Consider the input on string like n to the 1,000, 10,000, b to the 1,000, okay? Somehow, if you have 10 states, you're asked to correctly determine this. But how could you possibly do this? You're not going to be able to, somehow you need to keep track of the number of A's and make sure that you accept exactly that. Because A to the n, B to the n must be accepted, but somehow A to the n, B to the n minus 1, the thing right before it, must be rejected, and the thing right, and the right after it must also be rejected, right? So somehow, exactly A to the n, B to the n must be accepted, but A to the n, B to the n minus 1, the one right before it must be rejected, and the one after it must be rejected. And exactly that must be accepted. How can you do that with finitely many states? You can't. So rather than saying, obviously, well, I don't know how to do it, so obviously it can't be done, that's not a very proof way. The pumping lemma just formalizes this kind of argument. It's like everything wrapped up in a nice package, like here's the way you can prove a language is not regular. So there is no DFA for certain problems. In some sense, that means it requires more than constant memory in this limited read-left-only model, you know. For example, how would you implement this in a read? Let's say I forced you to use a for loop that reads left to right, and you can't do anything else for loop-wise. How could you determine this? Give me an algorithm that decides this language.
What do you mean? Like store?
Suppose you do. What was your question?
I was gonna say, what do you mean by decide?
Like on input a string, you give me pseudocode that says yes or no.
Oh, gotcha. Sorry, I don't know if I interrupted you.
What were you saying?
I was asking about the clarification if you had actual memory.
Okay, yeah, sure. Let's say you have some memory.
Just read left to right, count the number of A's, and then count the number of B's.
How would you count the number of A's?
Go left to right, maybe like I guess a while loop to iterate through it.
It's simpler than that. Yeah.
While or for loop.
Use a variable to keep track of how many A's.
Counter plus plus, see an A. If I see a B, counter minus minus. If I ever see an after that, return false. But if I count the number of A's, plus plus, count the number of B's, minus minus, that'll do it. That takes approximately like log n bits. Can that be done with constantly many states? No, turns out. We'll prove that today, in fact. But before we do so, we need to formalize the pumping lemma. The pumping lemma basically says that languages that are regular, ones accepted by DFAs, NFAs, regular expressions, are highly patterned. They're very, very repetitive. And they all follow from this thing, which is the pigeonhole principle. If you have n plus 1 pigeons, n holes, and you assign the pigeons into holes, some hole has greater than or equal to 2 pigeons. This is all the pigeonhole principle states, right? We can in fact apply the pigeonhole principle directly to infinite regular languages, right? Here's the reason. The NFA only has, excuse me, let's say DFA. DFA only has finitely many states. You are asked, but it's asked a difficult job. Finitely many states correctly somehow decide an infinite language. So you may only have 10 states, but you somehow need to behave correctly on strings of length a billion, trillion, really, really long strings. So we're asking a lot of a DFA. So if W has a certain length, we'll say in a second, and the number of states is equal to, let's say, P, how long should W be to ensure that a state is repeated in the computation? Before we get to that, let's just say how many states are visited in the computation? At most. Not perhaps at least, but at most. Yeah,
P is
almost, it's off by one.
P minus 1.
The other way. Let's say W has length P. Okay, let's say it's exactly the number of states. If the length of W is 2, you visit 3 states.
Oh, plus 1 for the starting state.
Yeah, basically. 2 transitions is 3 states, right, at most. So if W is equal to, if the length of W is P, and there are P states, then P plus 1 states are visited during the computation, right? So in the computation, if P plus 1 states are visited, but we know that we only have P states, what do we know must be true by the pigeonhole principle?
That state was revisited.
Yes, some state has been visited twice. So let me give you the picture of what that really means. So if some state has been visited twice, suppose it looks like this. Suppose this is not only just a sequence of states, but a sequence of transitions that gets you to an accept state. Let's say this is the state that has been visited twice. Let's call this X, let's call this Y, and let's call this Z, okay? So, if the size of Q is equal to P, and the length of XYZ exceeds P, some state is visited twice. So what do we know about the paths in the graphs? If XYZ is an L, then what do we know also must be an L? On some surgery, yeah.
X, Y star, Z.
I'll say XZ is an L, XYYZ is an L, and for all I, which is a natural number, including 0, XY to the I, Z is an element of L. What this effectively means is if a DFA, and this, it does matter for this time, if a DFA accepts a long enough string, if it's longer than the number of states, or exactly the number of states, because it'll visit plus 1 transitions, right? If it's the number of states, then some substring of it can be infinitely copied and pasted within the string, repeated. And all those strings will also be accepted. So in fact, if one string is accepted by the DFA, then infinitely many other strings are also accepted that all look like this, right? So in fact, there is this highly repetitive pattern in every regular language, right? It's highly patterned, lots of pattern. Now this quote-unquote loop here, Y, it could be one state, it could be a self loop of the state, it could be like 10 states here, it could be any kind of combination of things. But just by the pigeonhole principle, we know some state is visited twice. So suppose the path from that state back to itself is what we call y, right? This is the intuition behind the pumping lemma. First we'll say why regular languages are pumpable, right? Questions on this intuition first. Yes?
We're talking about inputs that are accepted
Yes.
only in this
Yes.
case? Okay.
Because, so like, we want to talk about the language, it turns out, so we'll pick strings that are accepted, and it's just convenient. Some of the decisions are not as general, but they're going to be made to make proofs easier. That's kind of what will happen.
Gotcha.
So let me give you the statement of the pumping lemma before we go on to actually like, there's two things we're going to do. We're going to give you the pumping lemma, and then we're going to give you how to actually use the pumping lemma. So this part is less important, but it's what the pumping lemma formula states, is that for all S is in L, with S greater than or equal to P, where P is the number of states of the regular language L. So like if L is regular, right, then there exists some x, y, z, such that S is equal to x, y, z. And then for all I, x, y to the I, z is in L. So we can say, and this is like, if a language is regular and it contains a string of length greater than or equal to P, then this holds, right? So if regular, then that means pumpable, right? We don't really care to show that a regular language is pumpable. We prefer to show the opposite, which is, what is the contrapositive of this statement?
If it's not pumpable, it's not regular.
Behold, we have a proof technique now to show a language is not regular. Just show it's not pumpable. If it's not pumpable, then it's not regular. Now, how do you show a language not to be pumpable? Here is how you actually apply the pumping lemma. The pumping lemma is complicated because there are a lot of quantifiers going along. So I'll give you the formula that you should write every pumping lemma proof in. It's easier to do it this way than try to figure it out by yourself. It is probably, you guys know these proof techniques, you guys know like induction, you guys know contradiction, you know all these kind of things. Pigeonhole arguments and so on. The pumping lemma is like a very niche proof technique, and it's kind of difficult and cumbersome to work with, and it shows only one thing, which is that it can prove a language not regular, right? So here's how you do it. Step one, assume to the contrary. Some language L is regular with pumping length P. What you're going to do is assume that L is regular, and further assume that L has P states. The DFA for L has P states. Now, P must be general. P cannot be 10. Because if you were to do a pumping lemma proof with 10, P equals 10, what you've actually proven is that there is no DFA of 10 states. What you're going to do is by assuming P is general, you show that P is insufficient. But because P is any number, there is no finite DFA of 10 states, of P states. So that's insufficient. So you can't assume P is 3 or 10 or something. It's going to assume there is no DFA of 3 states or 10 states. So let P be general. 2, consider S in L such that the length of S is greater than or equal to P, right? So this is something smart. You get to choose, this is like for all P exists some S with some conditions. You get to choose the S, and that'll be very important later on. 3, for all possible x, y, z, such that S is equal to x, y, z, subject to the length of x, y is less than or equal to P, and the length of y is greater than 0. This is a little complicated, but this is again a for all x, y, z statement, right? So you have some nesting, quantifier nesting going on here. First off, why are these assumptions we can make? Why must y be greater than 0? Why must the length of y be greater than 0?
Because of the way the loop works, even if it's a self loop.
when would y be 0? Length 0, what does that mean?
There is no loop in which.
Yeah, it'd be like an epsilon transition, you'd have something like. And in fact, just trivially, you can always kind of pump that. We want to show that you can't pump it, right? So like that doesn't help us. We want to pump something non-trivial. So this just says, why is something meaty? There's nothing, we're not pumping zeros in there, okay? I mean, we're not pumping like the empty string over and over. We're pumping something actually there. That's all that says. The second condition, xy is less than or equal to p. Why is that true? Why can we assume that? That's a difficult thing, yeah.
Because of pigeonhole principle
Yeah.
and how if there's more than p, then it's not going to be able to be accepted.
Yeah. So think of x, y, z again as a path in the DFA, right? Now, by the pigeonhole principle, there could be multiple. Certainly, some repetition must occur if s is long enough, but there could be multiple times, right? It could be happening at the first character and the last character and everything in between. Who knows? And in fact, the self loop could even have a self loop itself, right? That's totally feasible. All this ensures is that x, y, and z are what we call them. Y, in the computation of x, y, z on the DFA, we know that by the pigeonhole principle, even if the string is extremely long, that a quote-unquote collision occurs in the first p symbols because you visit p+1 states. So you are guaranteed by the last symbol of y that there must exist a repetition. Now, it can occur before then, but you're guaranteed by the last symbol of y that such a thing must occur. And all this basically says is that y corresponds to the loop that we are calling it. That's all that enforces. Right? It's an extra assumption that we get to make, which will simplify proofs, it turns out. Questions on that? Yes?
So in this case, xy is literally xy.
Yeah. Like the xyz is 3. When we write s equals xyz, we mean that we split s up into 3 pieces that are joined to each other. Xy is the first part, and then whatever comes after y is z. When we do some examples, I think it'll become clear. Okay. Step 4. Choose I, which is not 1, and show that x, y to the I, z is not an element of L. So again, this here is then an exists I statement, right? So you choose I and show that x, y to the I, z is not an element of L, and by doing so, you have proven that the language is not pumpable and therefore it's not regular. So if you can follow these steps, and we'll do the rest of the day today will be spent on examples. You follow these steps, you can prove a language is not regular pretty easy, right? Questions on just the proof outline before how to do the proof before we get into just doing the examples of the proof, right? Yes?
We have to do it for all x and y's, right?
That will be difficult, yes. That will be that's the difficult part because you get to choose S, but then you don't get to choose how it's split up. That's going to make a lot of cases. So for each case, you choose a different I perhaps, but this will enumerate several cases. You'll see why this will be difficult. But what's cool is you can make this part less difficult by choosing a better S. So, but there's some optimality that can be done here. And let's do some examples before we talk about them, right? Questions on that? More questions on the outline?
So this is sort of like a proof by contradiction?
Mm-hmm. Assume to the contrary it is pumpable, then every string can be pumped. But we found one string that cannot be pumped. Contradiction. No matter how you broke it up, it couldn't be pumped. Okay? Trying to make sure that the thing aligns perfectly. Okay. Let's prove the language as we described 0 to the n, 1 to the n, and as a natural number. And instead of a and b, let's use 0 and 1. Okay, so it'll just be, we can use a and b as variables, as we'll see. We prove this language is not regular. Assume to the contrary. It is regular. With pumping length p. Consider what S? Give me any S in this language. Give me a string in this language. Now this is a difficult question if you haven't seen how to do it before. Give me an S in this language that has length greater than P. Yeah.
0, 1, 1.
But what if P is a billion? Actually, in 0, 1, 1 would also not be there. It should be 0, 0, 1, 1.
Okay.
We want the number of zeros to be equal to the number of ones, right?
Oh, yep.
Yep.
So, 0 to the P, 1 to the P, 0, 1.
Just that.
Just that.
Yes. Right. First off, notice that S is an L. And that the length of S exceeds P. In fact, the length of S is 2P, so certainly it exceeds P. Okay. Now that's basically how you got to do it each time. You're going to choose the length of S as a function of P in some way. It'll be done this way, right? You may want to try like 0 to the P over 2, 1 to the P over 2. Who cares? It's fine. And in fact, this is better, as you'll see in a second. For all cases, for all x, y, z, such that S is equal to x, y to the x, y, z with the length of x, y less than or equal to P, and y, the length of y exceeds 0, we have really only one case. X is equal to 0 to the a, y is equal to 0 to the b, and then z is equal to 0 to the p minus a minus b, 1 to the p, with a plus b to be less than or equal to p, and b to be greater than 0. Now, this is a non-trivial thing. This is quote-unquote one case, but it's actually multiple cases as a function of p. But what's going on here? To just give you kind of an aside explanation, we have 0, 0, 1, 1, okay? This is S. And this is some p here, right? It's of length 2p, and it looks like this, right? But if xy must be less than or equal to p, then we know no matter how we split up S, it looks something like this, right? If there are p zeros and xy is less than or equal to p, then y or x can't contain any of the ones. It's the prefix, so it's somewhere over here, right? Perhaps it's all of them. If x plus y, if xy is equal, the length of xy is p, then it's all of them. But it's never any of the ones, because the first one occurs at the p plus 1th character, right? So it's somewhere in here. So we'll just call this 0, we'll call this one, we'll say this has length a, we'll say this has length b, and we'll say z has length p minus a minus b, which is this thing, and then 1 to the p, which is this thing, right? So z is just whatever is left over. This illustration is not part of the proof, but it's just like explaining like why we split it up like this, what can happen. Now these two conditions just enforce a plus b is less than p, and b is greater than 0, just enforce the thing that we want it to be, right? Okay, so we really have one case. It's really a function of the p cases, but consider I is equal, give me an I that's not 1.
2.
Yeah. Then x y to the I z is equal to x y y z, which is equal to, what is x y y z? We're going to have 0 to the a. Then we have two copies of y, which is 0 to the b, 0 to the b. This is x, y, y, right? Then we're going to have z, which is 0 to the p minus a minus b, 1 to the p. And this here is z, right? But what is that? If we were to simplify some exponents, we can concatenate things. This is going to be 0 to the what? 1 to the p.
0 to the p plus b,
Yeah.
which is not in L.
Yeah. Since b is greater than 0, p plus b does not equal p. So x, y, y, z is not an element of L, and L is not regular. QED. Let's talk about the details of the proof and like how this maps to the argument we've done previously. What we said here is, suppose that there is a DFA. Consider a string that is twice the length of the number of states, right? Then it should be the case that we'll exhaust a bunch of zeros. In just the zero portion of the string, we'll reach some state twice, okay? We'll have some self loop, but the self loop will come way before only taking the zero transitions. By choosing I equals 2, what we're actually saying is we're only taking this loop twice. So we add an additional cycle exactly once. So we go x, y, y, z. So let's just consider we add the self loop one more time. The self loop, as we've defined it in our variables, has exactly length b. So what we're doing is adding exactly b more zeros. And we say this would be an accepting path, just b more zeros. But the problem is that shouldn't be accepting contradiction. That's sort of like how this proof maps back to the combinatorial argument inside the DFA structure, right? But this is our first example of a pumping lemma proof. Questions on that one? The rest of today, again, will be spent on many more examples, so. Excellent. Let's do another one. Okay. Another classic non-regular language is the language of even-length palindromes. WWR, W is in sigma star. Where WR means the reversal of the string. So we take a string and we concatenate it with its reversal. That's all this means. So this contains all even-length palindromes. Intuitively, you should also believe this is non-regular for the same way A to the n, B to the n is non-regular. If I asked you for an algorithm to determine this language, what would it be? Give me an algorithm that loops left to right over the string and decides this language. Yeah.
You use a DP algorithm that checks to make sure that the length, I'm not sure if the indexing is right, but so that when you check the first index A, when you reach halfway through the string, the next one should be A as well.
Well, it's going to be the reversal of it. We'll talk about WW in a second. So it's in fact, the first one is the last one, and so on, right? Mm-hmm. Now, even if you assume you can't jump back and forth, what you could do is like write down W, then when you're at the halfway point, read back W in the reverse order. Maybe you put a stack, actually. You put W into the stack, you're at the halfway point, and you pop off W to read the next couple characters, make sure those are equal. Either way, doesn't appear you can do it with finitely many states, right? Similar intuition behind A to the and B to the end, but of course we can formalize it with the proof. Assume to the contrary. L is regular with pumping length P. Consider S is equal to what? Give me a even length palindrome that's length greater than P. Another important thing is that you want to choose a language, a string, that is highly sensitive in the sense that any perturbance to it would probably bring it out of the language. So there are always strings that you could pump, it turns out, that are bad choices of S. Here's a bad choice of S. 0 to the P, 0 to the P. That's not going to work, because if you do copy and paste an even amount in there, you'll accidentally still be a palindrome. So that doesn't work. This one's not a good idea.
Can I do 0 to the P, 1, 1, 0 to the P?
That'll work. Now, I'm going to actually do a bad idea on purpose, just so we can see what happens. So that's in fact, the correct solution. But let's do 0 to the P minus 1, 1, 1, 0 to the P minus 1, okay? He said 0 to the P, 1, 1, 0 to the P. And now that'll make the proof much simpler. But I'm going to make the proof worse on purpose so we can see what happens, okay? Notice that, let's just make our sanity checks. Is S an element of L? Yes. Is the length of S greater than or equal to P? The length of S here is 2P, so in fact that does work. All right. Consider for all x comma y comma z, such that S is equal to x, y, z, subject to the length of x, y is less than or equal to P, and y exceeds 0. We have two cases, in fact. This is choosing a bad S. I now have an additional case. Case 1. X is equal to 0 to the A, y is equal to 0 to the B, and then z is equal to 0 to the P minus A minus B, 1 to the 1, 0 to the P. Minus 1, okay, yeah. Case 1 is that y does not contain any p's, okay? Case 2, the length of xy is equal to p. Then we have x is equal to 0 to the a. Since y is not empty, it could have up to 0 b's, but it must have at least one a. Y is equal to 0 to the b1, and then z is equal to 1, 0 to the p minus 1. Right. Check me on that. Any issues with that? What are the conditions here? Here the conditions are that a plus b must be less than p and b exceeds 0. Here the conditions are a plus b is equal to p and b exceeds 0. Right? Those are the two cases. Basically, whether or not y exceeds, whether or not y contains that 1, which is the pth character. It's allowed to now because this is p minus 1. Right? So for case 1, consider I equals what? Not 1. Give me an I.
3.
3? I don't want to do the work for 3. Let's just do 2. Okay? 2 will be easier. Let's do 3. Fine, let's do 3. Okay. I don't want to do 2 mistakes and 2 extra long steps to the proof. But let me just show you what will happen, okay? If I equals 3, then x, y to the I, z will equal x, y, 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 z, which will be 0 to the a, 0 to the b, 0 to the b, 0 to the b, 0 to the p minus a minus b minus 1, 1, 1, 0 to the p minus 1, which is going to be 0 to the, what is that? P minus 1 plus 2b, 1, 1, 0 to the p minus 1, okay? We went around by I equals 3, we went around the loop 3 times. So there's an additional 2 times that we went around it. So we have a plus 2b here instead of a plus b. If we had I equals 2, this would have been b. Because if I equals 3, that's a 2b now, okay? Since 2b exceeds 0, what's our contradiction here? It's a little difficult to formalize, but we see this is obviously not a palindrome of even length. Why?
The ones are off center.
Yeah. So if I were to formalize this more, what I would say is if you cut the string in half, the first half could end with a 0. The second half has 2 1s. The first half has 0 1s. So certainly it can't be a reverse palindrome, right? So the second half having 2 1s and the first half having no 1s means it's not a palindrome. So we see that x, y cubed, z is not enough. Okay. For case 2, consider I is equal to what? Maybe I'll do an interesting I as well so we make things
0.
Yeah, let's try 0. This is called pumping down. Then x, y to the I, z is equal to xz, which is equal to 0 to the a. We forget y, just ignore it. and then z here, which is going to be 1, 0 to the p minus 1. Now, a could be p minus 1. So that's not immediately a contradiction, but there's another contradiction here.
It's not even. There's only one.
Exactly. Since xz has an odd number of 1s, it cannot be an even length palindrome. Since for all cases we have found an I such that xy to the iz is not an element of L, so here this would say xz is not an element of L, right? Then, thus, L is not regular. QED. Done. Questions on that? Again, a classic canonical non-regular language, right? A little kind of worry we took some detours just to show you more details about what the proofs could look like. Yes?
Then why is p minus 1 like a bad choice for?
Simply because I have this extra case here. I have to consider all options, including the situation when y equals 1, when y contains a 1, right? If I were to draw this out, it would look like, right? So it could be the case that this is the y. And then we have to somehow make sure that that case is covered. We can't just say, oh, it's always going to be true that y is no 1s. Now, if we had a p here instead of a p minus 1, this would be big enough that xy less than or equal to p, y could never contain the 1. But there is a case that y contains a 1. And in fact, for even worse choices, you could have y be anywhere in it if you don't do it right. If you don't choose the first block to be less than p, terrible things can happen. You could have all kinds of complicated stuff. It could accidentally be pumpable. Right? Questions on this? Let's redo the proof, actually, and just make it easier. So by redo the proof, we're actually going to do it for a different language. Consider the other, this is the third canonical non-regular language. WW, such that W is an element of sigma star. Now this isn't like anything in sigma star concatenated with anything with sigma star. This is specifically things concatenated with itself, which is different than sigma star. This is not sigma star, because that's all possible pairs. This is only the pairs of things concatenated with itself. So this contains like the empty string 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, and so on, right? So it contains things like that. But the proof that it's not regular, in fact, is almost the same, except for the reversal. So let's just continue with it. Assume to the contrary. L is regular with pumping length P. Consider consider S is equal to, and let's, instead of choosing a bad S, let's choose the good S. So it's going to be 0 to the P, and instead of WWR, it's just WW here. So this is going to be 0 to the P1, 0 to the P1, right? To account for the W and the W. Certainly, we see that S is an element of L, and that the length of S exceeds P, right? We have one case for all x, y, z, such that S is equal to x, y, z, subject to x, y is less than or equal to P, and the length of y exceeds 0. We have a single case, which is that x is equal to 0 to the A, y is equal to 0 to the B, and then z is equal to 0 to the P minus A minus B, 1, 0 to the P, 1. Right? Consider, give me an I. Yeah. We have xy to the IZ is equal to xyyz, which is equal to 0 to the A, 0 to the B, 0 to the B, 0 to the p minus a minus b, 1, 0 to the p, 1, which is going to be 0 to the p plus b, 1, 0 to the p, 1. Right. We've inflated again the 0 block at the beginning by p b's. We've taken that y loop one additional time. Now, what's our contradiction here? How are we going to show this is not of the form WW? It's a very complicated thing, actually. Yeah.
Since b is greater than 0, p plus b is greater than p, which means that it's not even, or not even, but I guess it would have to be even, right? So it's not an even number.
Yeah, you have the intuition, and it's like obviously not of the form WW, but we need to certify it a little bit. So here's what I would say. I mean, like, we could just say we're done there, honestly, but let's make sure we are. Suppose that 0 to the p plus b, 1, 0 to the p, 1 is equal to W1. Sorry, I'll do it this way. If b is odd, then x, y squared z has odd length, and we are done. So suppose b is even, then suppose that 0 to the p plus b, 1, 0 to the p, 1 is equal to W1, W2 with the length of W1 is equal to the length of W2. So just take the string, it's even length, we can cut it in half. Name those two halves W1 and W2. Even though they have the same length, why are they not equal?
W1 will have 0 ones, and then W2 will have 2 ones.
Yes.
So it's the same argument for the palindrome.
Since b is greater than 0, W1 has no zeros, but W2 has 2. So W1 does not equal W2. Then x, y squared z is not an element of L, thus L is not regular. Done. I spent a little more time for clarity on the extra sentence at the bottom, but would you agree that this proof is simpler than that proof? The cases matter, and sometimes a bad S can mean an exponential explosion in the number of cases. You can have a bad S, and then you can suddenly have 6 cases to work with. And if you miss a case, the proof is technically incorrect, because it has to be for all possible x and y, z. So what you gotta get good at is choosing an S. If you choose an S well, the proof is basically, I mean, it's like easy to memorize. You just go bing, bang, bing, and it's over with. So choosing a good S in the beginning just like makes everything nice. And I'll give you an example today where choosing an S is not easy, right? More questions on this proof?
Does this cover all the cases?
Ah, yes. Now technically,
S equals 0 to the p, 1, 0 to the p.
yes, technically there is a number of cases, but those cases are all the same because x and y are all zeros. We chose a good S. Such that this has length p. So if x, y come before, they can only be like this. Right? Y can never be anything but zeros. Same with x. Just by the fact that x and y come at the beginning of the string. Right? The first symbol of x happens to be the first symbol of s, and so on, right? So no matter how you split up the string, if x, y is length less than or equal to p, this is somewhere in the beginning. Right? So we call it one case, but it's really like a function of the number of cases of p, where a plus b sum to p less than or equal to p, you know, whatever, right? But really they all look the same. So we call it one case, but it's really some function of p cases. All right? Yeah, let's do. Okay, let's do another example of a unary language. A language is unary if its strings are all the same symbol, right? So we're gonna do 1 to the n squared. N is a natural number. So this is strings of all ones that have quadratic length. 1, 2, 4, 8, no, that's powers of 2, my bad. What is it? 1, so it's going to contain what? The empty string, 1 squared, what is that? 4, 9, 4, 7, right? Something like this. The length of the strings is going to grow quadratically, right? And we showed how to make DFAs for like the linear arithmetic progressions, right? 1 to the an plus b, we can do those. So it turns out that if you have a function that's like monotonically increasing in some way, like in a way that's super linear, too bad, it's not regular. So this, in fact, the DFAs can do like linear looking stuff. They can't do like quadratic looking stuff. You can't have anything funky in there, so to speak, right? And the contradiction we'll have to reach is going to be a little, take a little second for us to argue about, but let's just proceed with the proof. Assume to the contrary. L is regular with pumping length P. Consider, I'll use some space up here. Consider S is equal to what? Give me an S in this language that has length greater than P. Yeah.
1p.
Well, what if P is less than, how do we know P is a perfect square?
Gotcha.
1 to the power p squared.
That's the best we can ask for. Let it be the number of states squared, okay? Notice that S is an element of L, and the length of S is equal to P squared, which exceeds P, right? P is the length of something, so it's going to be a natural number, right? Forget the 0 states. It's going to be something real. It's a real natural number, so it's like, it's definitely greater than or equal to P, right? Consider, for all cases, such that x, y, z is equal to S with the length of xy less than or equal to P and the length of y greater than 0, we have that x is equal to 1 to the a, y is equal to 1 to the b, and then z is going to be equal to 1 to the p squared minus a minus b. Right? Consider I is equal to what? Give me something, give me an I.
2.
Let's do the small one. I equals 2. Then x y to the I z is equal to x y y z, which is going to be equal to 1 to the a, 1 to the b, 1 to the b, 1 to the p squared minus a minus b, which is equal to 1 to the p squared plus b. Right. Okay. Why is that not in the language? That's the part that's going to take us a second to argue about.
Length of y is greater than 0. No, sorry, it's
not trivial, actually.
xy is less than or equal to p. So that means that y, the length of y must be less than or equal to p. So b is less than or equal to p. The next perfect square would be p plus 1 parentheses squared, which is p squared plus 2p plus 1. P is less than 2p plus 1, so therefore it doesn't actually reach the next perfect square.
Let's formalize that. Here in our cases, we know that a plus b is less than or equal to p, and we know that b exceeds 0, right? Here's the thing. Since a plus b is less than or equal to p, then we know that b is less than or equal to p. These are all lengths of strings. So if the sum of these two things is less than this, then each of the parts must be also less than this. So we know this is true, right? So p squared plus b must be less than or equal to p squared plus p, right? Now, p squared plus p is actually just less than or equal to p squared plus P plus P plus 1. If I just add on the positive term, this inequality becomes an equality, right? But P squared plus P plus 1 is what? P squared plus 2P plus 1, which is just what?
P plus 1 squared.
Yes. So, P squared plus B is strictly less than P plus 1 squared. Okay, we've done the first thing. The second thing is, what do we know about B?
Greater than 0.
Yeah, since B exceeds 0, we also know that P squared plus B is strictly greater than P squared. Thus, the length of 1 to the P squared is strictly less than the length of 1 to the P squared plus B, which is strictly less than the next square, which is P squared plus P plus 1 squared. Since the length of our pumped string falls between two consecutive perfect squares, of course it can't be a perfect square, because the next perfect square is this one. It's not this one, we pumped away from it, but we will never reach the next perfect square, right? It's too far away. Thus, x, y squared, z is not an L, and L is not regular. Let's describe in a little more detail, like, what part of this proof, if any of it, corresponds to the DFA, right? Essentially what happens is these perfect squares have gaps that are growing, right? The difference between two perfect squares increases. So what it means is that because the gaps increase, for any number of states, there is a gap that's larger than it. So if some DFA, so like let's say you have a gap that's like length 100, there is no DFA that can go from an accept state on P squared, not hit another accepting state before the 100th thing, right? The gaps are growing too far. Something like this. So for any number of states, there will be a gap that's big enough that it will get messed up on. That's kind of all this really formalizes is, right? It hits an accept state, but the number of states is so little that the gap is big enough that it'll reach an incorrect accept state before it reaches the next correct accept state, because these are increasing away from each other. That's kind of what's going on here, right? Questions on this one? Unary languages usually follow some similar arguments like this, right? Choosing S and X in the cases, that always gets trivial, but then everything else can be a little complicated. Okay, let's do one more quickly. Let's do 0 to the A, 1 to the B, such that A and B are relatively prime. Okay, we all recall what that means, relatively prime numbers, 2050 level stuff, right? They share no common divisors, whatever, right? Except one. Challenging string. We somehow need a string in the language, okay? Such that A and B have to be relatively prime. But when we perturb them, somehow they will no longer be relatively prime. How do we do this? It's going to be a very creative choice, but I'll show you a complex example. Assume to the contrary. L is regular with pumping length P. Consider We need somehow the GCD of these two things to be, yes?
Can I do B equals 2 and then right?
Yes, we'll do B, we'll do that, but we need to first make S. So this is the hard part, and then we'll get to the,
Okay.
yeah. So what S would work here?
0 to the p, 1 to the p plus 1.
Let's try that. 0 to the P, 1 to the P plus 1. Okay. We're not doing the proof yet, let's just do some work. And by the way, it's helpful when you write proofs to do each proof 3 times. First, convince yourself it's true. The second time, you kind of formalize it a little better. And then when the proofs you actually turn in, the proofs you actually write, have to be formal. They're like a certificate of authenticity. So a lot of times you do your scratch work, you don't do it in the proof. When I'm teaching on the board, I'm explaining the steps and so on. It's not part of the proof. But let's suppose we did this. Now, if we pumped up or down, let's say we pumped down, we would have what? P minus B and P plus 1. We need to ensure that somehow that these are definitely relatively prime. Fine. But these, how do we know these are not relatively prime? We need to ensure that one divides the other or something like this. Complicated. Do we have another idea on how to choose an S?
I feel like pumping up might be easier.
So let's try to pump up.
Then, well, actually, it has to depend on B. If B is
Yeah, exactly. It's a complicated
has to be relatively prime to P for you to actually be able to get something that's.
I don't think anyone would come up with the correct S. It's too complicated, but that's kind of why I'm showing this to you. But if we have another guess, you know. Okay, here I'll consider S is equal to, what was it? 0 to the Q, 1 to the Q minus 1 factorial, where Q is the next prime, which is greater than P. Okay. Suppose Q is the next prime greater than P. Certainly, the GCD of Q and Q minus 1 factorial is what?
1.
Yeah, these are going to be relatively, Q minus 1 factorial is 1 times 2 times 3 times 4 times all the way to Q minus 1. And since Q is prime, it can't be represented by a product of any combination of those. So certainly this is going to be 1, so S is an L. And S, the length of S, I don't even want to compute it, but it's definitely length greater than P, just by definition. Why? We said Q to be the prime bigger than P. Fine. What cases do we have? We have all the same cases. We have for all x, comma y, comma z, such that S is equal to xyz, subject to xy less than or equal to P, and the length of y exceeds 0, we have x is equal to 0 to the A, y is equal to 0 to the B, z is equal to 0 to the P minus A minus B, no, sorry, q to the q minus A minus B, 1 to the q minus 1 factorial with A plus B less than or equal to P, and B greater than 0. What do we have next? We have, consider something simple. Consider what I?
Yeah.
That will actually, that's the only one that won't work. Sometimes you have it where only a specific I works. In fact, there's another proof I didn't do it today, but like only one I works, it turns out. All the others accidentally are correct. They pump the string. We want a single I that doesn't pump the string.
0.
It's gonna be 0. Then xz is equal to 0 to the A, 0 to the q minus A minus B, 1 to the q minus 1 factorial, which is equal to 0 to the q minus B, 1 to the q minus 1 factorial. Now, is the string in L or not? Since B exceeds 0, we know that q minus B is less than or equal to q minus 1, right? So, the GCD of q minus b and q minus 1 factorial is equal to what?
Q minus 1 factorial over Q minus B?
It's, it'll be simpler than that, I think.
Oh wait, no, it's Q minus B.
Yeah, it's just gonna be that factor. Right. It's gonna be represented in that product somewhere. So take that out. Now, we also know what? Since b is less than, since a plus b is less than p, we know that b is less than or equal to p. So we know that since q exceeds p, we know b is less than q, right? So q minus b is greater than 1. Thus, xz is not an element of L, and L is not regular. It's easy. Done. Complex example, would not expect you to come up with this, but just notice some details. The argument is a little non-trivial. Constructing S is very non-trivial. You kind of have to know how the whole proof is going to work out when you construct S. You can't just sit down and bang this out in one thing. You kind of have to like work out all the little details. And choosing this S, basically the whole proof works on that. No other choice of S is going to really make any sense or work there. So like, this is just an example of something complicated that would have to be done. Yes?
If B is less than Q, how do we go from that to Q minus B greater than 1?
If B is less than P, then B is also less than Q. So what we don't want is for this to be accidentally 1, right? We want it to be something else, not the factor remaining that's just 1. So it has to be something else. Where this was, because GCD of 1 with anything would be 1, right? So this can't be, we don't want this to be 1. We want this to not be 1. So we just say, since B is strictly less than Q, then Q minus B must exceed 1.
Isn't it possible for B to just be Q minus 1?
Oh, hold on.
You said, say, if P is,
Yeah, I see what you're saying.
yeah, if P is Q minus 1, then it would be possible for B to be equal to Q minus 1.
Yes, that would, how do we fix this? Let Q be the second biggest prime. Repeat the whole thing, pretend I did that correctly. Pumping is complicated. It's like, for all exist, they're nested. Students get confused all the time in the steps. It's a very delicate technique. And as you see, I did make a mistake here. So, suppose it works though. Questions? All right.